So let us start with the discussion on charge distribution in the nucleus. Okay, now basically we will be probing our nucleus with electrons. So if this is the nucleus, then basically we will be sending in electrons here to probe the distribution of charges inside the nucleus. How the charge is distributed? Is it in the center, or it is uniformly distributed, or there is some other sort of distribution? Okay, something like that. Now you see, we already know that regarding nuclear force very much less is known. However, we know a lot regarding the electromagnetic force, and this is the reason for sending in electron. Why? Because this electron is an electromagnetic probe. Okay, and as a result, the protons and neutrons which are inside the nucleus will not act upon it. Therefore, since the protons and neutrons will not act on the electron, so basically we will get the electromagnetic charge distribution. There is nothing regarding nuclear force coming into play. So I am just going to talk about basically EM probe I am sending, and I am going to probe the again charge, which is basically a feature of electromagnetic force, right? Now such type of experiments, high energy electrons on nuclei, has been done by Hofstadter and his group, right, at the Stanford Linear Accelerator. Now to do that, the first thing that we have to keep in mind is the de Broglie wavelength, right? So de Broglie wavelength of electrons. Now for kinetic energy of electrons, approximately, so for kinetic energy around 500 MeV, you can check for yourself from this expression of de Broglie wavelength that the lambda dB for electrons, it comes around 0.4 fermi-meter, and this is good enough to probe the nucleus, right? So this means that this is the energy of electrons that we are going to talk about. Fine, good. So now let's talk about the experiment. So okay, so here you can see experimental cross sections for different electron energies. These are the various electron energies: 84 MeV, 126. Slowly the energy is increasing. Now the first thing is, suppose this is the nucleus, right, and I am sending in electrons from here. So what will happen? Right now think of Coulomb interaction only, right? No nuclear interaction, because this is electromagnetic flow. Now Coulomb interaction, so this means Rutherford scattering cross section, our graduation day stuff. Even schools nowadays we learn about this. Rutherford scattering cross section comes into play, or basically the Rutherford scattering comes into play. So what will happen? Some of the electrons will basically get diverted like this. There will be no interaction also. So basically what we are going to talk about is the angular distribution, you see, or basically we are going to talk about measuring the scattering cross section. So we are going to measure how many electrons have scattered at this particular angle by putting detector at various angles, right? These are the detectors. Okay, so by putting detectors at different angles, we will be able to do measurements of scattering cross sections as a function of scattering angle. Now this is the measurement that has been done over here. Okay, along with that, what we have done, you see, now you look into these measurements. See, what do you observe? Slowly, first thing that you notice is this over here. The energy is slowly increasing, right? 84 MeV, 126 MeV. So, at lower energies, the graph is almost like a straight line or so. But as we go to higher energies, something changes. You see, there is kink. You can observe. See here. You can observe this kink. See here. This entire region. You can observe some sort of kink. So basically, when do you observe this? You observe with increasing energy, or that is basically decreasing de Broglie wavelength, and then you observe the first diffraction minima, and that shift towards the smaller scattering angles. This is basically a diffraction minima. We will talk about it. But right now what I am going to tell you is the observation. So you see this thing. You observe this thing. So what we are observing is decreasing de Broglie wavelength. The first diffraction minima, it gradually shifts towards smaller scattering angles. This is the observation that we are getting. Now let us try to explain these observations. Okay. So the first thing we are going to do, basically we are interested in finding the relation. So this is what we are going to do. Just a second. Yes. Yeah, here. We are basically going to derive the relation between angular distribution, which is basically delta n theta, of the scattered electrons and the charge distribution. Okay, so this is what we aim to do today. Now, the first thing that we observe, that the deflection of an electron passing through a charge distribution. Let me show you. Just a second. Yes, here. So this is basically a charge distribution that you can see. Yes. So what I was saying is, we are going to observe the deflection of an electron passing through a charge distribution. This is more or less the charge distribution. I'll be explaining the various concepts very soon. Now, if we have the charge distribution, this rho e, then this deflection depends on the momentum transferred to the electron, and that momentum transferred is this delta p. See here, delta p. And what is this delta p equal to? P minus p prime, or p prime minus p, or basically where p is the momentum of the incident electron and p prime is the momentum of the scattered electron. Now remember that for elastic scattering, we have, they both become equal, right? And so from this relation we will get very simple, from trigonometric analysis, this particular relation for sine theta by 2. Okay, now let's go to the next step. What is the step? So this is the relation which we just derived. And now this is our Rutherford scattering formula that we know. See, 1 by sine 4 theta by 2, 1 by E0 square, and all the other constants. So now we are going to put this relation into this, and as a result we are getting this relationship, d sigma d omega. Again, this is all Coulomb interaction, nothing else. Now, very important thing to note that this equation is valid for the scattering of a point charge with mass m. So everything is good. Why should we worry? Now remember, we are talking about this thing, right? So our aim is basically, let me show you. Now, if the nucleus is a point charge, then the scattering we will get as a result the d sigma d omega only Rutherford. Okay? This is what we will get if the nucleus is a point charge. However, we do know that nucleus is not a point charge. However, it has got an extended distribution inside the nucleus, various, right? And as a result, this thing will be modified, and the modification will be due to this distribution of charge distribution. You understand the actual problem? If the entire charge is concentrated at a point, then we will only observe this. However, the charge is actually distributed inside the nucleus, and as a result this we will not observe entirely. However, but a modification needs to be applied. This will be somewhat modified. And what's the how do you know? You might ask me, sir, how do you know that we need the modification? These things, you see, the minima, all these things, they in fact show that there is a charge distribution itself. Okay, so now how do we proceed? Good. So let's now start the investigation for the finite charge distribution of the nucleus. Okay, so what do you see on your screen is basically, so this is basically my entire nucleus. Just a second. The charge distribution, you can say, inside the entire nucleus. This is the center of the nucleus, and I am considering just a volume element dV having charge dq, which is rho e into dV, right? And this r is the distance. This volume charge is at a distance r from the center of the nucleus. So what I am going to do? Well, I am sending in basically electrons, right? So basically I am going to describe the incident electron beam by plane wave. So this is my plane matter wave, which represents the incident electron beam, and this impinges on, say, one of the volume element, and later on we will integrate over the entire volume. So right now let us consider the effect of this incident plane matter wave on a random arbitrarily put volume element. Okay, so this is how we will do. Fine. So, and also note that these are the two relations we get from the vector. So this distance r, this is k prime, this is r prime, and this is at a r distance, and this is the point of observation P. So next, now you see, as a result of this scattering, basically, yes, so you will find these notes later on. Good. Okay, so see what is happening is this, yeah, so this is my nucleus, the plane wave electron, the plane electron wave is coming, right? Now as a result, there will be some interaction with the charge distribution of the nucleus, and the electron wave will be scattered off, right? So this scattered spherical matter, see, the incoming is a plane wave, however the outgoing is a spherical matter wave, and this spherical matter wave I am representing like this. Okay, now what's the observation at this observation point P? What happens? Let's see. So at the observation point P, the amplitude A of the scattered spherical matter, which is this one, in the observation point P at distance r. Again, what is the distance r? This was the distance r. Now obviously when we are going to observe and do the measurements, we are not going to do this at Fermi meter distance or at angstrom distance. We are going to do at our own convenient distance, which is of the order of meter, even centimeter or so. The detector will be placed at a distance of few meters or few centimeter from the point of experiment. ठीक है? So this means that this entire dimension is of the order of Fermi meter. However, this r will be of the order of meter or centimeter. Fine. So basically infinity in a way. However, so basically what I want to say is that the r, this r will be much greater than the nuclear radius, and as a result the amplitude A we can write like this. See here, phi 0 into e to the power I k r, A by r prime into e to the power I k prime into r prime, where the factor, this small factor A, basically this, let me write it down, this small factor A depends on dq and the scattering cross section d sigma d omega. This small factor A depends on this too. Now previously from the last figure we already observed these things. So if I incorporate these two relationships, and I will get this term modified as this, in this way, then I can write in a more convenient manner like this. Again, for r, point of observation much greater than the small r, and here k prime is virtually parallel to r. Let me show you the figure again. What was k prime? This was k prime. So if r is very large, then k prime becomes roughly parallel to r. Okay. So in this case, so basically, just a second, yes. So basically with k prime equal to k equal to just k, so we can replace e to the power I k prime r into e to the power I k dot r, right? And so from the previous relationship, this relationship here, we will get this relation, A equal to this. So there are basically three terms over here: first part, second part, and then third part. Okay, now what I am going to do, that I previously told you, the basic logic was this: consider plane matter wave on the electron. On the effect we will study on a very particular volume element dV, and then we will consider the scattered wave effect, and later on we will do the integration over the entire volume. So this is what we are doing now. So integrating over all volume elements dV, we will get this result, where this dr is basically equal to dx dy dz, and q is the total charge. So q is the total charge. Okay, now you see here we have got basically two terms. This is the first term and this is the second term, right? The first factor describes the spherical wave scattered by a point charge. So scattering of spherical wave by a point charge. What is that? That is ZE, right? At center r equal to 0. So this will be observed if only the point charge ZE was present. Remember, this is what I was saying. And what is the second term? This second term is the modification due to the charge distribution. So this second factor, this takes into account the finite charge distribution. Finite charge distribution within nucleus. Okay. Now, so for differential scattering cross section, which is proportional to the square of the scattering amplitude, we get this relationship where delta P is equal to H cross into delta K. Now what I am going to do is, if I use this abbreviation instead of the Rutherford scattering cross section, then we have got this modification. So what I am saying is that previously we have only this term. Now because of the presence of this term, the entire d sigma d omega or the differential cross section changes. So this was my previous differential cross section, the first term, and now we have got this modification due to the charge distribution. So product of two terms. See, and this term, the second term, this is known as form factor. So this is the form factor. This is basically the Fourier transform of the charge distribution, rho CR. Now interestingly, you see this form factor, let us observe its effect. So again, for the sake of my students, so again this is a nucleus, roughly classical view. Now inside the nucleus we can have protons and neutrons, only two species. So suppose these are protons, and again we have got, say, some other color, let me use, yes, this, and these are neutrons.
স্ক্রিনটা তো দেখতে পাচ্ছি না স্যার।
Okay. So yes, this was what I was telling you. The reds are protons, greens are neutrons inside the nucleus. Now these neutrons, they have got no charge. Fine. And we also know that there are more neutrons compared to protons for medium and heavy nuclei. And these protons are all positively charged, whereas neutrons have no charge at all. Now these protons, how they will be distributed inside the nucleus, whether the picture is like this that I have shown here, or it will be somewhat different. Yes, so the question is, how will be they distributed? So is it like that they cluster together in some particular place, and the protons are clustering like this and the neutrons are clustering in a different way? What do you think? Can such a thing happen?
না স্যার।
Why not, sir? Why not? There is always a possibility. In fact, remember in the class I was talking about collectivity, how it starts when more and more nuclei they are excited, right? Now such a case can happen when protons and neutrons they vibrate against each other. Okay, so there is a sort of vibration like this where protons are here, neutrons are here, and then they can overall vibrate among themselves like this. This is also a sort of collective vibration. There are situations like this, but not in normal nuclei, only particular nuclei which behave in this vibrational mode. This is a mode of vibration. Normal nuclei, we have got situation like this, but there are collective excited nuclei. When you excite certain nuclei, they behave like this. Now the question is, how do I know this when I excite a nuclei? By doing scattering experiments. And this is what I am discussing the theory. বুঝতে পারছো? The charge distribution can change inside a nucleus if I excite the nucleus. Now the question is, how do I know this? Only by doing scattering experiment. আমি নিজের হাতে দেখতে পারবো না. The nucleus is not like a cake or pizza that I can see and tell you that, well, the toppings are more on this side than on that side. The chicken is more on the left side or so. It's not going to work like that. So I have to rely on experiments, scattering experiments. They will tell me whether the situation is like this or there is an unequal charge distribution. Okay, so this is why we are studying. The reason is there are a large variety of nuclei out there which when they get excited they behave differently. Understand? This is the importance of studying this particular form factor. This is how we are going to observe the effect. Yes, so this is what we were discussing. Fourier transform of the charge distribution ρ. Now, how does this form factor look like? Let me show you. Yes. So here you can see the experimental plots of the scattering cross section d sigma d omega for scattering of fast electrons at gold nuclei. So basically this I am showing you the result from the experimental d sigma d omega. This is experimental. From there I am showing you the variation of this form factor as a function of delta k. Okay, this is basically from the data by Hofstadter and his group. You know which year it was? It was around 1963 or so. Also remember this. Now, the first thing, what do you note? The first thing that you note is that the form factor decreases with increasing momentum transfer. So, this form factor, let me use a different color. Yes. Okay. So, the first thing you note is form factor decreases with increasing momentum transfer delta p. Right. Next, what do you observe? The first is decrease. There is a decreasing trend. Next, you see maxima minima, like this stuff. Okay, you are also seeing this. So the distinct minima we also observe, distinct minima of cross section at high energies of projectile. And what is this? This is basically this thing. Hey, kothay gelo? This thing is basically due to diffraction at finite charge distribution. So matter waves are incoming, they are seeing an obstacle. The obstacle is quite substantial charge distribution. So matter wave is electromagnetic. It is observing obstacle which is also electromagnetic in nature. And as a result, what happens? There is diffraction. Simple thing. Light waves, matter waves. Light waves can undergo diffraction. Here matter waves are undergoing diffraction. Okay. Remember this thing. This very presence of minima, diffraction minima here, they are always absent for the case of scattering from a point charge. So present only for charge distribution and absent for scattering from point charge. So this is only due to the result of charge distribution. Fine. Now let me consider again. Okay, next page. So basically the first term, so let me write it down. So basically this was my term d sigma d omega at an angle theta. This is equal to d sigma d omega Coulomb. This is the first term into your F rho delta K whole square. Right. Now you see this differential cross section decreases with increasing energy of incident electrons. This differential cross section decreases with increasing energy of incident electrons. Why? Because this first factor over here, this describes the Coulomb scattering, and this is proportional to 1 by E0 square. Okay. And also this decrease, the reason is that this form factor, this also decreases with increasing momentum transfer delta P. Note that at fixed scattering angle theta, basically we have delta P is of the order of P, which is just classical relation. Now before I finish this part, you see these oscillations in the curve of this d sigma d omega, basically they become more and more distinct with increasing energy. Remember, this was the first thing that we talked about. The oscillations, they become more distinct with increasing energy as the energy increases. See over here, as the energy increases, they become more and more tilted. There is a very little change over here. Okay. So basically this means that decreasing the de Broglie wavelength, they become more and more distinct. The first minima, basically here, if this is the first minima, then the first minima shifts to smaller scattering angles theta. Fine. Now let us consider a little bit more detail. You see, when the incident particles are described by their de Broglie wavelength lambda dB, say for example here the incident particle is described by their, this is what we are doing, right, is de Broglie wavelength, then the first minima appears, this I will discuss more on in next class. Then this first minima basically appears for a diameter d of the target nucleus at an angle phi minimum, for which we have this condition phi minimum equal to lambda dB by capital D. And in this case there are always pairs of scattered particles with such a path difference. What is the path difference then? It is equal to basically lambda dB by 2, and their wave functions had opposite phases and they cancel each other out. Okay, so this is what we have covered today regarding the charge distribution, and we have discussed mainly about the form factor, and so in the next class we will discuss more about this. Okay, so with these basic ideas, now here I am showing you the experimental results of the radial charge distribution. So this is the radial charge distribution for some of the nuclei. Of course, these are based on the measurements by Hofstadter's group. Okay, now these experiments have confirmed that basically the charge distribution have a slightly different radial dependence than the mass distribution. Remember, the mass distribution is somewhat different, ringing as something like this for most of the nuclei, but here you see for some this is the nature is different. For helium it is different. See, for hydrogen the nature is somewhat different, for helium it is different. So this is what I am saying. The charge distributions generally have a slightly different radial dependence than the mass distribution. And what is the reason, do you think? The reason is basically the Coulomb repulsion between the charged protons, which pushes the protons more to the edge of the neutron. বুঝতে পারছো what is happening? So basically, if this is my nucleus, then because of the Coulomb interaction, the neutrons will be gathered more towards the center, whereas the protons, they will be pushed more towards the surface, so that the Coulomb repulsion between them gets minimized. Now the experiments also show that the charge distribution of many heavy nuclei are not spherically symmetric. They are in fact not spherically symmetric.